I'm just wondering. That would make
Can you hear me? You can't hear me? Doing mechanics. Yes.
So, like, there's like cost intervals and stuff. If we had now 200, could we do it with those instead of the calculations otherwise?
Sure. I mean, I don't care which way you do it.
You know what I'm saying? Like, the way that we've been doing it otherwise is kind of like not faking it, but kind of like we know how to do it otherwise. Can we do it real?
Yeah. I mean, I guess I'm just worried about. I mean, some of these are very easy visual, and I don't think you have enough information in the given problem to write out an equation and calculate it like you might do in a math class. So I'm not sure if that would help, but yes, definitely.
I'm saying if it came to a problem where
Sure.
we did have enough,
Sure.
it would make it longer otherwise to calculate.
Sure.
Some of the other problems, like if it's chapter 23, we have to do
Right.
it was trying to do Jacobian and we did some other weird things, we could just do Jacobian.
Yeah, and that could be right, and that could be said if you.
It's like some weird lambda switch where you can really just do Jacobian and you just be like, oh.
Yeah, but if you're. I guess my concern is if you're missing that, the Jacobian is just something you should be able to see visually in it. So
instead of going through like 5 steps, we can just see it.
yeah, exactly. So whatever is the easiest for you. If I'm going through and it's on a test, if it's valid, that's fine. If it's using math that's not really taught because it's above this level, that's fine. All right, well, I guess it is start time. So, I will get us started, I think. So, I'm glad you guys are full of energy today. So, let's talk about the electric potential again. Because here's the point of this chapter. The point of this chapter is to get you to... Thanks, Aaron. The point of this chapter is to get you to find out what is the electric potential. And I'll start off with just a quick review of last time, what I tried to work in there in the last 40 minutes I think we had as we did some example problems still from 24 and took a little bit of extra time. But this is what I was trying to get across here, is that the change in electric potential can start off with this idea that it's the change in the electric potential energy per charge. So the U, as you might remember from Physics 121, is a symbol that we use to represent the energy. And so we're going to switch it over here to a V when we're talking about the potential. And the first warning I was trying to give you was don't confuse potential energy with potential. They are closely tied together, and when you know one, you also know the other, and that is really going to be the strength of this, because we had this little diagram here, which I will add back, that said, all right, from our mechanics, we know that if you have the velocity, you can get the position, or the other way around, since they're, this is our mechanics, they're related by derivatives and integrals, and then this was related from the net force. And so that was all of our mechanics, our Physics 121. And then again, what we've done up to this point was to say we would like to know what the field is. Because if you know the field, you can easily get the force. This was the easy part of our last two chapters. This was the part where you just took the charge and multiplied it by the electric field to get the force. The harder part, the part that we've really been focusing on, the learning here, was to say you could know the electric field from a single point charge, and then any object can then be chopped up into an infinite number of pieces and come up with the total electric field. So again, that was chapter 23, that was Coulomb's law. We followed that here with the idea of electrical flux, and that if you calculated the electrical flux, if you created a surface and the charge inside, blah, 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 you can get the electric field also. And so again, chapter 23, 24. Now in 25 here, and I'm going to put it right above, is we have this idea, and first from mechanics, that if you know the energy, and of course in mechanics it was kinetic energy, 1/2 mv squared, and gravitational potential energy like mgy, or if it was, out of the atmosphere, we had that negative g, the universal gravitational constant, mass 1, mass 2 divided by the radius. So we used the principle of conservation of energy to find speed. We also said by taking the spatial derivative of it, you could get to forces, if you remember that from 121. And that, hopefully, you'll see again today, because I am going to put just right above it this whole idea of potential. And I'm going to leave this diagram here because I want you to see, here's the game I'm going to play today. And what you're going to do over the weekend on the homework is find the potential. Because when you know the potential, you can get to potential energy. That's what this statement is saying. This statement is saying it's not going to be a difficult step to get to potential energy if you know potential. So the real key here is, how do I get the potential? Because once I know that, I can get to potential energy in the same way I can get to force. It's not a hard step, it's just how much charge you are there. And that's why I said a few moments ago, I want to hopefully make sure that what you got out of last lecture here is electric potential is close, but not quite the same as electric potential energy. And so when you know one, you multiply by how much charge. And so you are really saying, and when you say electric potential, you're saying how much energy do you have per charge, right? And so the units we used were voltage. And so if I look at this wall plug, as we talked about, and we said, okay, that wall plug is 120 volts. Or if you open the hood on your car, you'll see this big battery in there, and you'll go, oh, it's a 12-volt battery. And that 12-volt battery means that if 1 coulomb of charge were to come out of that battery, that would give you 12 joules of energy. And of course, being a big car battery, when you go to start it, let's say, it's a lot more than 1 coulomb. But for every coulomb, you get 12 joules of energy. And that was this idea of voltage, that you can then measure potential in a unit of volts. Okay? And so more on that as we go forward. But also, haven't really shown it to you yet, haven't really even shown you the conservation of energy, but just like you could take the derivative of energy to get force, you're going to see that we could take the spatial derivative of potential to get electric field. And so if I hopefully get nothing else across here on how to solve these problems, at least I hopefully will get the big point across here is, this is why potential is going to be very powerful. It's going to be a nice way to either find the velocity of an object using the principles of energy and conservation of energy, or it's going to be a nice way to also find the electric field, which can lead back to force and acceleration and velocity also. And so our little strategy of getting to what is the position of these electrical charges, or how fast are they going, can be approached either by an energy approach or by an electric field force approach, just like we had in our mechanics. And so now we're getting pretty sophisticated, which is why we're quickly approaching a practical application in the next chapter. We're going to build some capacitors, get started with some electronics. We'll be ready for a test real soon here as we finally have 3 weeks and under our belt here and have this idea. So, we left off then with expanding that out. We left off by saying, all right, if you have, here's our definition of the change in potential, which is the change in potential energy per charge. Then I'll leave the per charge alone for a second, but this was an integral from some initial to final, negative of an integral, of force dot dr. And if this is electrical forces, which is what we are talking about, then we can write that as the charge times the electric field. And now you can see the whole purpose of putting it as a quotient of the charge. It drops away, and we left with this little integral that the electric field then, or the change as we add up the electric field over some position, is what we mean by the change in voltage. And we had a simple picture, and the lab we did, or 2/3 of you have done, 1/3 of you will still need to do the lab today. But we had this parallel plate here, and we had an electric field, and I left you with this question. I said, if you're kind of imagining a point in the middle, say the initial point, and if it helps, I like to mentally think about it's me. It's me standing in the middle of this plate. There would be a value for the energy or the potential at that point. And then it would either increase or decrease depending on which way I moved. And that's what this integral is trying to say. It's the same integral we did when we did potential energies back when we did Physics 121. So if I am standing here and I move with the field this way, so let's say this becomes my final point, what is this integral saying? Will there be a change in the potential? Yeah, will it be an increase or a decrease? Yeah, and you guys got it'll be a decrease because this dot product means cosine of the angle between them. And so as we move with the field, we will be going down in potential. What if we move the other way around? What if we again started here and moved in that direction? And I'll call that my final point. Would the potential change? Yes. Would it be an increase or a decrease? Yeah, it would be an increase because, again, we are going against the field, and you can see that this angle then would be 180 degrees, and that negative together with that negative makes a positive. And so I am saying here that there are points in space, just like we did for mechanics, there are points in space where we could say this is the potential energy, this is potential energy, this is potential energy. And so as this object moves up against the force of gravity, it's more potential energy. As the object moves down, it has less potential energy. What if the object moves sideways? What if it moves this way? What's the change in potential? Yeah, exactly. 0. You can see it in the math because it's cosine of 90 degrees. And of course, those of you who already did the lab, that was a big focus on the lab. To say that there are surfaces, which in this case would be a plane right in the center, which we will call equipotential surface. That would all be at the same potential. And if you were to move closer to one plate or the other, and in this case closer to the negative plate, you would go down in potential. Closer to the positive plate, you would go up in potential. But anywhere along this plane that is cut right in the center, parallel to these other plates, then you would have the same potential. And so we called those equipotential. And notice they're perpendicular to each other, and hopefully now you see why. Conceptually it is, look, you wouldn't change energy unless there was a force either acting with you or against you as you moved. And that's why when you move perpendicular, you don't change your energy. There's no component of the force. Now with all that said, what I did not say, and want to make sure you catch here, because it's a little different here than gravity. If I were to put a positive charge here, what would happen to it? Wouldn't it go towards this negative plate? So this object, as it would naturally move, would it go to higher or lower potentials? It would go to lower, right? Which, that probably isn't a surprise. I mean, if I just took an object and dropped it, you would say it naturally goes to a lower potential energy, right? What, though, if there was a negative here? Doesn't it go that way? So this negative goes opposite of the positive, right? Now, that doesn't surprise you, but here's my question. This thing goes naturally to higher or lower potentials?
Lower. Because it's a negative.
I'm glad I mentioned this. Didn't we say this was higher potential? Should we talk about it again? All right. Start here. If I go with the field, does the potential change? Yes, it goes down. If I go against the field, does the potential change? Yes, and it goes up. So make sure you catch this difference. This positive moves, in this case, to the right, lower potential. This negative moves which way? To the left, which is higher potentials. Now, don't confuse that with potential energy. Because how would I calculate the potential energy?
Oh, charge.
Change in potential energy has to do with the charge I put there. So if you look closely at this positive, you will see that the positive moves this way. Your change in potential is a negative. You multiply by a positive charge, and you're going to say that this object moves to lower potential energies. So that particle moves not only to lower potentials, but also to lower potential energies. But take a close look at the negative. The negative then moves this way. It moves to higher potentials. This number is positive. But it's a negative charge. So what's the change in potential energy? Negative. So this object moves to lower potential energies, right? And so again, we did not have that issue when we dealt with gravity, which is why when we dealt with gravity, we never dealt with a difference between the potential energies of it and the potential of it. We just said, look, they're one and the same. But when you have something more complex, where, like I said, gravity only does one thing. It just sucks and pulls together. But these electrical charges both suck and repel, and so we got to have a way to deal with that, and that's what the potential is doing. That's why it was so nice to talk about the electric field, because the electric field had a defined direction regardless of what kind of charge you put there. The force was in different directions depending if you put a positive or a negative in the field. But the field was well defined on its own. That's the big advantage. And the same thing here. That's why potentials will be of a much more advantage, and we will talk and calculate them, not the energy. Now we're eventually going to have to get to the energy. But that's going to be an easy mathematical step. You just multiply it by its charge. And that's why when you put something like this, you cannot look at this parallel plate and say which direction, left or right, is an increase in potential energy. Because it depends what charge you put there. But you can say which direction is an increase in the potential, not potential energy. So make sure you caught this, that both of these objects naturally move to a lower potential energy. It just happens to be in different directions. Okay? And like I said, that's just a little bit different than gravity. You don't naturally have that. Although if it helped, we can make something kind of similar to it if we add buoyancy to our gravity. For example, if I take a helium balloon and I let it go, because of the atmosphere, which way does it naturally go? Up. And believe it or not, that is lower potential energy, because as the balloon goes up, the atmosphere comes down. And the atmosphere has a higher density, and so more weight goes down than goes up. And the overall, when you add the balloon together with the buoyancy and the weight of the atmosphere, it is a lower potential energy. So you can kind of have an analogy. I probably should just stay away from that one and just say, look, it is a little different. And so some things are similar, but other things aren't. So here's what I want to do for the balance of today, and maybe even flow into Tuesday, depending on how far we get. Let's do some calculations. Now that I hopefully got the idea across, I want you to know why I care about this. Let's do some calculations. And probably the best thing to do is to start with the simplest case and ask this, okay, so what would be the potential from a single point charge? Let's start there. And those of you thinking ahead go, well, okay, single point charge does sound like an easy one, but why would I care about a single point charge? I mean, how many times am I going to really have just a single point charge? Well, the answer is probably never. But why would I still care about a single point charge? Exactly. The same reason I cared about it in Coulomb's law. If I know the electric field from a single point charge, couldn't I take any shape and chop it up and add them together? And therefore get the electric field from any shape? Yes. And guess what we're going to do? Exactly the same thing. We're going to find the potential from a single point charge. And everything we do from here on out is just going to think, well, you know, take that rod, take that disc, take that ring, take that sphere, take that shell, chop it into an infinite number of pieces and add it up. And other than doing some integrals and chopping it up, that's the most important key step, is I know the potential from a point charge. So, for the next 2 hours here, that's what we'll do here. So what is the electric potential? Maybe I should put from a point of charge Q. So we've been working with this quite a bit. I'll just put a little plus sign with a Q, and I got to give it some size on the board. But again, imagine it infinitely small here. And again, going back, you would say, okay, let's look then at the electric field that is then created by this thing. I'll put a little bit of an E there. Because what we have to work with here is that change in potential is the integral of this electric field. So let's actually do the integral here. Let's imagine, if you will, like we were kind of in that picture, saying this is my starting point. Right there. There is some point in space right here where I can say that it has a potential. And now if I were to move to another place, the potential might change depending on how I move. It may increase or decrease. If I were to move with the field, the potential would decrease. If I would move against the field, it would. And if I would move perpendicular to the field, it would stay the same. Exactly. So you got that point there. So to make my integral maybe as easy as possible, and maybe to get an understanding there, let me just move with the field here and see what I come up with. So this says that the change in potential is negative from some initial point to some final point of E dot dr. Okay. So I'll leave the negative alone there. Maybe I will call this radius initial and radius final. Since I'm talking about a point charge that has a field kind of in a spherical shape, I'll just say initial and final. I'll label them with an R, radius. Okay, that makes sense. But here's the big one. What's the equation for the electric field from a point charge? Okay, Coulomb's constant times the charge, Q, over R squared. Good. And then I'm going to be moving outward, so I'll call it dr. And like I said, to make it simple, I'm going to go straight out. So when I take the dot product, it would be cosine of 0, right? And so dr, am going to be moving in the direction of the field. Those two are in the same direction, straight out. Now, of course, I did it the easy way, kind of to the left, but it would be the same thing if I was going up or if it was on this side. I mean, I guess that's right. I'd go left here, I could go down there, but I'm moving with the field, okay? And of course, that cosine of 0 is 1, so I'll drop that off there. The Coulomb's constant, the charge, I'll put there. And then I have this integral from some initial to some final point of dr over r squared. And then, fortunately, that's not a hard integral to do. Like I said, it's why I kind of want to do this. It's not a hard one to get the equation for the potential of a point, and then, better still, if I have the equation for a point, I can do anything. And that's what I want you to see. All right, so what is this integral? Isn't it negative 1 over r? Again, evaluated from some initial to some final. And so, as I look at this, the two negatives cancel off, and I get a Coulomb's constant times the charge over the final radius minus a Coulomb's constant charge over the initial radius. And of course, what we mean by this change in potential is this is the final potential minus the initial. And so if we kind of match these together, we get what we're looking for here. What we're saying here is the potential from a single point charge then would have this form. Right? And so we don't have an r squared down here like we did for the electric field. And you can see why it went away. We did an integral, and so every time we do an integral, the exponent increases by 1. So when we had electric field, it was 1 over r squared. So now when we have potential, it's 1 over r. And hopefully it's not too much of a surprise, because didn't we see that same thing in mechanics? We saw the force of gravity as universal gravitational constant, the mass of the two objects, and on r squared. But when we did the potential energy, we got something that looked like that, where the force was an r squared, but the energy had a 1 over r. Okay? And in this case, the sign changed. We don't really have that here because our field is pointing outward instead of inward as in gravitation. So in that case, their sign doesn't change. But
how did you get Vf minus Vi equals dQ over Rf and that to the box?
So from here to here?
Yeah.
Okay, so you can see that I have an equation, right? That kind of looks like this twice, right? It has a final position minus an initial position. So what I'm really saying is this, the final, would be calculated based on final position. Okay? The initial would be calculated based on that. So just kind of generalizing it, what I'm saying is any point in space, A, so pick any point, you would calculate its potential by knowing its radius at A. And then I'm just dropping the A and saying, okay, now I have a generalized equation. So I actually did the integral from a limit beginning to end, but I'm more generalizing it by saying, okay, that would be the equation for the potential anywhere. And then if I moved from point A to point B, then I would have, a B minus an A. Okay, so I put a little box around it because, again, I can't overemphasize it. It's the same thing we saw in chapter 23. So don't be surprised as you see those same integrals, either easy or hard for you, where what we're going to do is we're going to take an object, we're going to chop it into a bunch of pieces, and we're going to find out from the potential, and from that we're going to get either the speed of an object that's moving using energy or the electric field. So, adding to this little place over here, I'm going to put V equals Coulomb's constant times Q over R. And put a little box around it. And so, I can spend the balance of today by saying, all right, let's look at some problems. Let's see the concept of potential All right? I'll leave that there. All right? So, let's watch this in work. Let's start with the easy case. One charge. All right? Let's do this. Let's say that I have a single positive charge Q. Okay? And I already know the equation for the potential. My first illustration is, could I use the potential to find the electric field? Yeah, let's do it. Now, maybe I better review some math that we saw again in Physics 121. I really haven't shown you here, but remember then, the potential is the integral negative of the electric field. Right? So if you look closely at this math, of course, this one, what I just did is I started with the electric field and got potential, right? I mean, isn't that how I got here? Okay, but what about the other way around? What if I know potential and I wanted to find the electric field? Well, I'm hoping you would see that what I just did was really an electric field in the radial direction integrated in the radial direction, right? Gave me the change in potential. And if it'll be okay, I'm just going to drop the delta here for a moment. How can I get rid of that integral? Take the derivative. So if I were to take the derivative of the potential with respect to r, and maybe I should pause here. I kind of used a different symbol than you are probably a little more common to see. And the same comment I made in Physics 121. For us, we're probably not going to make much of a distinction between it. Our math level here is Math 160 and below. But here's what this means. This means take the derivative with respect to r. But this means a little more tighter definition. It says don't let any other things change. Okay? Which, of course, remember, movement on a plane in polar coordinates, you could move in an r direction or you could move in a theta direction. Okay, so what this means is take the derivative with respect to r, and anything that would have an angle or a theta, ignore or treat it as a constant. All right, fair enough. Which in our equation, that's fine, because I only have things in r. I don't have anything in a theta. All right, and of course, if I did that derivative, I get that. Which, of course, means negative the derivative of the potential with respect to r would give me the electric field, at least the electric field in the radial direction. Now, maybe I should do this in Cartesian coordinates too, because I did this first step with saying, let's look at this integral in a more of a polar coordinate system, in a radial. But we could also write this equation as v equals, and we would have minus an integral, and in here, in this dot product, we would have the electric field and movement in the x direction, and the electric field in the y direction with movement in the y. And that's really two separate integrals now. This is an ex dx and an ey dy. And now you can begin to see why this whole idea of a partial derivative is a little bit more important, because if I wanted to know the electric field in the x direction, how can I solve for that one? Yeah, I need to take the derivative with respect to x. But there's a variation in y. But if I let y be treated as a constant, then what happens to this when I take a derivative? Yeah, it goes to 0. So the derivative of the potential with respect to x would give me a negative ex, and that then would be 0. And then moving the negative to the other side says that negative, the derivative of the potential with respect to x, would give me the x component of the electric field. And likewise, the negative, the derivative of the potential with respect to y, would give me the y component. Okay? And so again, depends how you want to find the electric field. Do you want to find the radial component, or do you want to find the x and y components, the Cartesian coordinates? It's kind of your choice which way you want to take the derivative. Obviously, it kind of depends on how you write out the equation. You could write it either way. What I have up here for a point charge is I have it written in polar coordinates, so I probably want to do that first. That's why I mentioned it first. But I do want to point out here that I could also do it in Cartesian coordinates. So I'll do an example next in Cartesian coordinates to show you that I can pick it either way I want. It's just a matter of what my preference is for my coordinate system. Yeah.
Just make sure the derivative, you do get a negative on those, correct?
Well,
It ends up being your negative electric field. Or
right. If I took the derivative, I get the negative of the field. So,
negative of the derivative.
right. Okay, so as I was hopefully will illustrate here for the balance of time that we have, is that if I know the potential, I claim I can use that in two different and useful directions. One direction is to take the potential and go this way to get the field. Another option is to use that in terms of energy to find the speed of something. And so coming back to this problem, knowing the equation for the potential, I could ask this question. Could I use this equation for potential? And could you then tell me what the electric field is from a point charge? Now, by the way, I hope you already know what the electric field from a point charge is. That's not what I'm trying to illustrate. I hope you know that. We've been doing that since the first day. Okay, but see how the math will work. Let's give it a try. I claim then that I can get the electric field in the radial direction if I go negative and take the derivative with respect to r of the potential. And the potential from a point is Coulomb's constant times Q over R. So I would get negative Coulomb constant times Q, and then I would take the derivative of 1 over R. What's the derivative of 1 over R? Negative 1 over R squared. The two negatives cancel off, and then I end up with something you're already familiar with. What is the value of the electric field? So if I didn't know the value of the electric field, I could now get it. So obviously, again, my point is, at this step anyway, is not really to find the electric field. We already knew what it would be, but to illustrate how it works and that we can do more complicated problems this way too. Ones where we really do not know the value of the electric field, and then we could use potential to find it. And that's what I was been saying, that we now have the skills to get the electric field three different ways. Coulomb's law, Gauss's law, and via the potential here. And that will actually wrap up our first three chapters on understanding the basic ideas of electricity and magnetism. And then we'll start getting into some applications. Why do we care about all these electric fields? How can we build useful things that can make the world better? Yeah.
So how do you know if you're going back to energy or you're finding acceleration that way?
Well, okay, depends what it's a big circle. I could go either way. My question for you was to find the electric field, so I knew I had to go this direction, right?
Yeah, I know, but when you derive the velocity.
Okay, then, okay. Let me be clear. At this point, there would be no velocity. There's nothing being pushed or pulled here. Okay? But I think the question you're asking is actually the one I want to calculate next is, what if I had an extension of this problem, and what I had was a point charge right here, call it Q, and next to it, starting a distance of r initial away, I put a charge Q prime. Should I call them 1 and 2? Would that be easier, or are you good with prime? I've been using Q. Oh, Q prime be okay? All right. Would be better? All right. All right. Oh, it kind of does look like a derivative. Okay. So I'll go 1 and 2. All right. So back here, this really meant charge number 1, which made electric field created from number 1. But let's just say for the sake of conversation that this number 1 is locked into place somehow. This is a charge sitting on an insulator. Maybe it's a big heavy insulator that it can't move, okay? But the other one is some other charge, maybe a single proton that's just out in space or somehow, or it's within my fluid that can flow there, and it can move, okay? Of course, physically, I think you know what would happen. What would happen if I set him there and then let him go? Yeah, well, this one can't move, but they are repelling each other. So what's this one going to do? It's going to go here, 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 here. And if there's no limit to it, and eventually this charge number 2 is going to be way over here somewhere, moving at some speed v, right? And that's my question. Could you tell me how fast that second charge is now moving away?
Can it roll from initial to infinity?
So I'm glad you say that, because as I look at this little diagram here, I know the potential, right? I use the potential over here to get electric field. Now, to be quite honest, even before I started this chapter, I knew how to get the electric field from a point charge. So before we even started this chapter, I could have said, what's the force between them? And then got the acceleration. Integrated that to get its velocity, right? Hard problem to do, though. Why? Is this a constant acceleration problem?
No.
It's not, is it? I mean, what happens as this object moves further and further away? Yeah, the force goes down, and hence the acceleration goes down. So yes, the object always goes faster and faster and faster, but the rate at which it goes faster is less and less and less. And to make matters worse, the rate that it accelerates is based on position, which I don't know because I don't know the velocity, but yet I have to integrate it with respect to time. So I want to integrate it with respect to time, but I really don't know where its position is with time. I only know its force rated to position. Ouch. Challenge. So what did we do about this problem back in mechanics? What did we do when we said if you wanted to find the velocity of something and you knew its acceleration in time versus its acceleration in position? What were our two options? We have the same two options. Remember, we can find the speed of something two different ways. Let's go back to our mechanics. If I hold something up here and I let it go, and I were to ask you, how fast is it going after 3 seconds? How do you solve a problem like that? With acceleration. You know the acceleration is 9.8, so you go 9.8 and 9.8 and 9.8, right? But on the other hand, if the question was different, I start up here, I let it go, how fast is it going after 3 meters? Then you used energy. Don't forget that. That was an important process in our mechanics, that we learned 2 important skills. We can get to velocity by either using acceleration, which is probably best done when you know things in time. But we can also get velocity by using energy, which is probably best done when we know things in position. Hence, this problem lays out nicely for energy, exactly. And so this problem is going to be really simple to do in terms of energy. And so those of you who said, well, I could just use Coulomb's law and integrate it, good luck, try it. Okay? And actually that one can be done. It's just not easy, but it really illustrates then that the reason we had these 2 skills in our mechanics, and the reason we have them again in the mechanics related to electricity, is that we're going to want to focus on, do we know things in terms of time? Well, then go this route to get velocity. But do we know things in terms of position? Then do it this way. And that's why we have the 2 principles: Newton's laws of motion and the conservation of energy and momentum principles. Sure, I'll say it's a differential equation, but that almost sounds like then you couldn't solve it unless you had your Math 220. And that's not true, because it is a first order differential equation that you can integrate. It just has time and position in, and you guys actually could do it with Math 160. It's just a really long way compared to what I tried to illustrate in 121 and trying to illustrate now is, let's do this approach. And then that will give me a chance to have shown you both approaches. And then I'll just keep doing the same thing again and again. Start with potential, and what could I find? I could either find the velocity based upon position here, or I can find electric field. So I already showed you how to find electric field. Let's answer this one now. This guy goes shooting off here, and it gets really, 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 really far away. What's its speed when it is really, really, really far away? Well, hopefully the first thing that comes to your mind is conservation of energy, right? When this thing is really, really, really far away, it has some speed, it has some kinetic energy. And so as we did in our mechanics, we can say the initial energy it starts with is equal to the final energy it starts with, or excuse me, ends with. If I go to the starting position here and I look at these two charges next to each other and ask what kind of energies do I have? I'll start with kinetic. Do I have any kinetic energy? No. So the problem started off by saying, let's put these two and let's hold them in place and let them go. So they start from rest. So I have no motion to begin with. Do they have any other energy? Yeah. And that's the new piece of our puzzle. They have electrical potential energy. And so how do I calculate the electric potential energy? Well, as we said here, if you know its potential, and you multiply by the charge, that will give you your potential energy. So, this is probably best written in a first step like that. It's the charge I'm going to place there, which is charge number 2. Right? That's what I'm placing it. I'm placing it where the voltage has been created by charge number 1. If I put those two together, I get charge number 2 multiplied by Coulomb's constant, charge number 1, divided by initial radius. And so that would be my equation for my energies to start with. And so that is our first example of calculating electric potential energy. And as I said, usually the hard part's right here, get the potential, because once you get that, all you got to do is multiply by that charge you're going to place there. Okay? And so that's my initial energy. What's my final energy? Well, clearly it's going to have some kinetic. That was the whole idea of the concept of it pushing, going faster and faster and faster. But I might ask, what about its electrical potential energy? Well, what do you notice here about the potential when you're really, 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 really far away?
It's so small.
Yeah, and so we're going to say, hey, it's gone really, really far away, and it's 0. And so this becomes 1/2 mv squared. Oh yeah, if it wasn't far away, if the problem said it's at some new radius r final, then this would of course be charge number 2, Coulomb's constant, charge number 1 over final radius, right? Yeah. Okay. But now I can solve this for velocity because I would then move the 2 to the other side. I'll write Coulomb's constant first. I have the product of charge 1 and charge 2. And then if I divide that by both the mass and the initial radius and take the square root, hope I did my algebra right, that was a bunch in one step there. But there would be the speed when it is really far away, right? And again, probably the simplest one we can do is this one, but I think it illustrates what I keep wanting to say, and we'll show you for the rest of the day. This is what we get the potential. Because when we get the potential, we can either take derivatives to get field, or we can find its energy, and from conservation of energy, get its speed. Right? And so that's the whole illustration. So let's expand this one. Now that I did a simple example with what I would call a single point, how about we do a dipole? What would a dipole look like? Well, why don't I put a grid on here? Maybe I better not put a dot in the center. I don't want you to think there's anything in the center. But if you remember that phrase dipole from before, what that means then is we've got a net charge of 0, but they're separated out here, right? And we did that like with the pith ball and the electroscope here. And so let me do this. Let me say that over here I have a positive Q that is then spread over to here with a minus Q. I mean, maybe this is a water molecule or something, right? Or some other molecule where the whole chemistry of it with the protons and the neutrons separate the charges out. So the whole molecule itself is neutral, but there's a separation of charge here. And we'll just say that this has moved over a distance a, and this has moved back a distance of a. So the whole molecule, if you will, is just 2a in length. And if we're talking about a molecule, that would be a small number. But again, I don't care if it's a molecule or not. I just want to illustrate this point here, that I would then have this separation of charge. And here's my first question for you. Could you use this idea of a point charge? Could you give me the potential anywhere on this plane? Way over here somewhere. Someplace at position XY. Whether it's in the first or second or third or fourth quadrant, doesn't matter. But if its coordinates are xy on a Cartesian coordinate. So let me take advantage of Cartesian coordinates now and the derivative with respect to x and y, so I can illustrate that one here. But if I had some point way out here away from the molecule, or even close to the molecule, could you tell me, first of all, the electric field? Now, to be quite honest, we did these kind of in Coulomb's law. We know what the electric field from a single point is, and we could probably just add the electric field from 2 points, although then we'd be adding vectors. So I'm not sure that doing what I'm about to do is easier than what we've already learned in chapter 23. But hopefully it illustrates the next step, and particularly the velocity step here, because you wouldn't want to do it with just Coulomb's law. You would want to do it with energy here. But if I were to say, what is the potential at that point, then I could say V total is the first point plus the second point. That's what I want to illustrate. Here's what you will really appreciate. The concept is the same we did with Coulomb's law, where we would add up the electric field. However, Coulomb's law, we were adding up vectors. And that means you have to pay attention to direction. Not only magnitude, but direction. If you didn't catch this, notice the potential and energy are scalars. There's no direction with them. Now, if you have an option of adding two things together, one of them involving direction, one of them not, what do you think might be easier? Yeah, one without direction. We don't have to worry about sine or cosine or any of those other pieces that we did back here with Coulomb's law. So as you'll see, this is pretty easy to get the equation for potential. Well, let's start with this one. Maybe I'll label it. This is 1, this is 2. So 1's going to be a little bit closer to me. How would I get the potential for that guy? Well, I guess it would be Coulomb's constant times the charge that's there. Okay. But how far away are you? Okay, good. So this is the distance away. Maybe I'll call R1 here. But in a Cartesian coordinates, you can see that it would be this distance squared and that distance squared, square rooted. Okay? So along the x-axis, how far is this? Yeah, it's x minus a. So I've got x minus a, and I'll square it. On the y-axis, how far am I? Y, so it's just y squared. And then I can go 1/2. So there it is. There's the potential from the first one. Okay? And so probably the hardest part here is the Pythagorean theorem. You got to get the horizontal distance, you got to get the vertical distance. Because the second one works out exactly the same way. I would add the second charge. But the second charge is negative. All right. So I put in a negative Q there, which kind of makes sense. So far we've been talking about positive charges, and they have made a positive potential. And so now a negative charge is exactly like that, but with a negative sign, so it's going to make negative potentials. Now, how far away am I from that one? Yeah, in this picture I might call it R2. But it is a little bit further, so you won't come out with 0 here. You wouldn't be, this number plus a negative of the same number. You're a little further. So I have a positive number added to a negative number, but the positive number is a little bit bigger than the absolute value of the negative one. So I'm going to have a value here. But as I heard some of you say, the horizontal distance would be x plus a. And I would square it. The vertical distance would still be y. And so there's my equation. Yeah. So some of you are saying 2a. No, x, I mean, if you put the origin here, it would be 2a. But of course, then this would have only been x. So either way it works. But splitting it down the middle gives me some symmetry that's going to make it a little easier when I do derivatives and integrals that you will hopefully notice here. All right. So, I have done the main thing I want you to see. Could you calculate the potential from 2 point charges? Yes. And now we can make the next step. Why would I care about it? Well, because it could give me the electric field, right? So, could I get the electric field anywhere on this plane? Yeah, in Cartesian coordinates. Sure. Now, it's going to take a little work taking derivatives. But I claim that I could get the x component and I could get the y component. I was going to put it over here, but maybe I should wait to see how much space I'm going to need to take the derivative, because that looks like it might be a little lengthy taking the derivative here. But I'll go ahead and take it. This should be minus the derivative with respect to x of the potential. And so maybe I'll start with the first term. Well, the first term is Coulomb's constant times the charge. And now I have to take a derivative of this thing. And probably the best way to think about this in the denominator is move it to the numerator and call it a negative 1/2. So it becomes a negative 1/2. And then you've got that same equation, but now to a 3/2 power, right? You have a negative 1/2 and then you lower the exponent by y1. So that's a negative 3/2, and I'll move it downstairs. But then we got the chain rule. And so the chain rule has a 2x minus a. And then the chain rule of that is just a 1, so I'll do nothing there. But that would be the first term. And the second term should be very similar to this. I would have the negative from here. I would have the Coulomb's constant Q. I then would take the derivative with respect to x. But this one looks a lot like that. Same idea, that I would then have a negative 1/2. When I bring down the exponent, this would make an x plus a squared over y squared to the 3/2 power. Then I would have a 2x plus a, and then another 1, taking the third composite function there. But there would be it. And I could simplify it a little bit. Oh, excuse me. And I forgot my negative sign, haven't I? I mean, that's just the derivative. This says it's the negative of the derivative. So I should have a negative in front of that and a negative in front of that. And so I can get the equation for the electric field in the x direction. It looks like those two negatives cancel off. That's good. And the 1/2 and the 2 cancel off. And I get Coulomb's constant times Q. I get x minus a. I get x minus a squared plus y squared to the 3/2 power here. And over here, those go away, and I get a minus, and I got Coulomb's constant times Q times x plus a over x plus a quantity squared y squared to the 3/2 power. So there would be the electric field in the x direction. And to be quite honest, not a surprise. I would have expected that with Coulomb's law, right? Coulomb's law, what I would have done right away is I would have put in the magnitude like this. And if I was doing this particle here, I would have done that for the magnitude. Then I would have multiplied by cosine of the angle, which would have been the adjacent, which is x minus a, over the hypotenuse. And I would have gotten that. And so that does give me the same as this. And for the second object, I would have done this. And so, again, not a surprise that I get exactly the same thing. As I said, it might have even been easier just to have done Coulomb's law for this problem because it's only 2 point charges. But my idea was to illustrate that I could get the electric field, right? I need to know the potential. So the real key to the problem of this chapter is know the potential, and then I can get the field by taking the derivative. Could I get the electric field in the y direction? Right, so minus the derivative with respect to y of the potential. And so let's try that one. And so the first term would become Coulomb's constant times q. Taking the derivative again would give me the negative 1/2 up there. It would give me the x minus a squared plus y squared now to the 3/2 power. Then I would have a chain rule, which would only be a 2y, since I'm taking it with respect to y this time, not an x. The negative from there would go here, and so just like we had up there, those two negatives will cancel off, and so will the 1/2 and the 2. The second term, I guess, would start off as a minus Coulomb's constant times q, but with that negative out in front, it would cancel it off. Then the derivative would be a negative 1/2. Then you would have the x plus a squared plus y squared to the 3/2 and the chain rule of 2y. And that would cancel off, and then we can have a negative out in front. So the equation for the electric field looks a lot like that one, in the sense that it is Coulomb's constant times q times y over x minus a squared plus y squared to the 3/2 power. And I believe this one's a minus, good, minus. And I've got Coulomb's constant times q over y, x plus a quantity squared plus y squared to the 3/2 power. Yay, there it is. Okay, and so again, if the question was find the electric field, I could. I've got the x component, I got the y components. And I can find it anywhere on here, right? And just to see if it works, let's do a couple of special cases here. What if we are talking about being on the x-axis? And so if we're looking at a point on the x-axis, what's the value of y? 0. Now, what would I kind of expect for the electric field on the x-axis? Well, I guess from this charge, I would expect it to be pointing to the right. Fair enough? And from this charge, I would expect it to be pointing to the left, right? So how much electric field would I expect in the y direction? None, right? Is that what I get? What's the electric field when y equals 0? 0. So on the x-axis, sure enough, the electric field comes out to be 0. Not surprised. Well, on the x-axis, the electric field in the x direction does not cancel off. I've got one going to the right and one going to the left, but I'm closer to the positive one. So I'd expect it to be slightly positive. And sure enough, if you look at this equation and put in y equals to 0, you get Coulomb's constant times charge. I'll leave this alone for just a second, because down here in the denominator, if y is 0, that goes away. That square with that 1/2 goes away. And I have x minus a cubed in the denominator, which cancels with 1 up there. So I have an x minus a squared. Which again, from Coulomb's law 2 chapters ago, hopefully doesn't surprise us, because isn't that what you would say the value of the electric field is? You would say it is the distance squared, and you're along the x-axis, so the distance would be x minus a, quantity squared. And so this one would have been really easy to do with Coulomb's law instead of taking the derivative and setting y equal to 0. Okay? Now the other term comes out to be exactly the same, where I have then again Coulomb's constant times the charge, and then I divide that by this term, but I'm setting y equal to 0 because I'm on the x-axis. And that square and half cancel off. There's a cube, goes with one of those. And not a surprise, I get x plus a quantity squared. So again, I don't know if these are good examples or not, but I thought they would be great ones to, hey, take the derivative and you'll get the electric field. And in this case, there were ones we already knew what the answer was supposed to be, so we can see if we are doing it right, if it's making sense to us. And it is. I could do it on the y-axis. What if you're on the y-axis? Well, of course, if you're on the y-axis, x equals 0, right? And so keep that in mind as we do the math, but conceptually, as I stand over here along the y-axis, somewhere over here, I would have expected the electric field from this one to look like this, right? And the electric field from this one, well, that wasn't really kind of away from it, so maybe more like that. And this one towards it, more like that. But looking at those two vectors added together, I'm kind of expecting that the vertical components are going to cancel off, right? Now let's take a look at the math. If you take a look at the math here, when you set x equal to 0 down here, don't these denominators become the same thing? So don't you have that number minus the same number? And so it comes out to be 0. So EY comes out to be 0 in that case. A little different reason why. There are two fields that cancel instead of the first case where each one would not even have had a component, but this one they do have a component. They just have to be equal and opposite, and they cancel off. And so up here we got a 0, but over here we get a 0. And the electric field in the x direction looks like it would be just the electric field in the x direction from one of them doubled up. And so again, I would expect these to come out to be the same. And they do. When you put in here x equals to 0, you can see that this numerator becomes the same and this denominator becomes the same. And in fact, the denominator just becomes an a squared plus a y squared to the 3/2 power. And the numerator just becomes Coulomb's constant times charge times A. It does have a negative in front for each term, so there's two of them. There's a negative from this one, and then of course you got the negative in there when you set that equal to 0. And so there would be the electric field along the x-axis. Yeah?
Wouldn't the denominator be minus a squared?
Okay, it's minus a squared, but minus a squared is the same as plus a squared. Right? Minus a. Right. So this term here becomes the same as that term. What was the other question?
So it's on y-axis, but you write it at y equals 0.
Yeah, I'm on the y-axis. And on the y-axis, x equals 0. And if I put x equal to 0 in here, this down here becomes a squared plus y squared, which is what this becomes. So they have the same denominator. And then the numerator is the same with a minus sign. So that minus that. A minus a is 0. Yeah.
Have you not used y and
E.
No, I mean on the left part of
E x. No, that's it. Here? No, I think this is right. Right? If the electric field in the y direction on the y-axis. Right, so when I'm on the y-axis, I will get an electric field from the first one that way, which has an up component, yes. But the electric field from the other one points down. Those two components put together give you 0, and that's what you're seeing. That component's the same as that component. They add together, they give you 0. Right? Now, like I said, so far anything that I've really kind of shown you, you probably would have done electric fields with Coulomb's law. But what you wouldn't have done is find the speed. Let's change this up a little bit now. Now that we've done all this, here, let's come back to this picture. Maybe I'll change colors a little bit since it's getting kind of messy in here. Why don't we do this? Here's this molecule again. So I'll kind of circle it in green there. And it's a dipole molecule. Let's just say that right here at some position x naught, I put a charge of positive q by it. Now let's talk about it conceptually. What will happen to it? Will it get pushed away, pulled towards it, or nothing? It should get pushed away, right? I mean, this would be our answer. We're along the x-axis. According to it being along the x-axis, we get no electric field in the y direction, but we do have an electric field on the x-axis, right? And it points slightly in the positive direction. And that fits hopefully our conceptual model that I am close to this positive, which is pushing it away. Of course, this negative is pulling it in, but the negative's a little bit further away. So I would expect this to be pushed away and always be pushed away. So again, back to the same problem. Could I ask you this? If I started at rest, I have a water molecule and I put a positive charge near it. I let it go. Now let's just say the water molecule can't move. What would happen to this one? It would go away, 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 away. And my question is, what will be its speed eventually? When it gets really far away, what is its speed? Can you do that one? And that's this other loop, right? When we know potential, we can either get the field, which I've been showing you with derivatives, or this next question, we can use potential energy and conservation of energy to get its speed. So let's give it a try. Let's give it the same type of fundamental principle. Maybe this is a good time to sell my point again. What's physics about? What's on the top of all your tests and on the syllabus? Right, knowing how to apply a few fundamental principles to explain a universal phenomenon. Now, okay. So, I am going to, again, leave this here on the board. This is the working equation for this problem. This is the key that I'm trying to illustrate. You know this, which I should emphasize I got from just adding 2 point charges together. So if you know how to do a point charge, you know how to do 2 point charges. When you got the 2 point charges, or 3 or 4 or infinite, you can then either take derivatives to get the field, or you can use energy to get speed. And that's what I'm going to have here. I've got a adjacent particle to it that's going to take off, and so I can apply conservation of energy. So I can say initial energy is equal to final energy. And like we just did on the one before, hopefully you're seeing it's the same type of problem. Not that I want you to be bored, but I'm hoping he doesn't need to do that. I can do it. Good. Because you're asked to do it, I think, about 20 times on the homework. The same thing again and again and again, right? And so here is this. What is my initial energy? Okay? And so I am going to take a charge Q. And I'm going to put it near this other Q. So that means if I were to take the potential that I have, which is Coulomb's constant Q x minus a squared plus y squared to the 1/2 power, and I multiply it by Q, that is my particle that's going to move, test particle Q, that is then at position x naught. So I'm going to put x naught there, and I'm going to put 0 there. That would be the equation from this one right here, the potential from that guy. And the potential from this one is a minus Coulomb's constant times Q, and I'll just start by writing the same thing that I have over there for the general equation for the potential anywhere. But I am putting a second charge, Q, at a position of x naught 0. And its kinetic energy is 0 if I say, let's, start with it right there. And so I think this simplifies a little bit. Well, maybe not. The denominator is slightly different. And so I will end up with Coulomb's constant Q squared in the numerator. And downstairs, it looks like I've got just an x minus a. Whereas the other term has a minus Coulomb's constant Q squared x naught plus a. And so that's the potential energy created by the closer one, the positive. This is the potential energy created by the second one. Together, that's the total potential energy. As they move away, or as one of them moves away, the other one stays put. But as this one goes away, way out here, what happens to the potential energy when it gets really, really far away? Yeah, hopefully you're seeing when x gets really, 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 really big, millions of miles, that's 0. So we have no more potential energy. No more potential and no more potential energy. Of course, where did all that energy go? Into kinetic energy. And so that's this whole illustration, that I can take the potential from there, get potential energy, use conservation of energy to get an equation that has a v in it for velocity. And so, one more step, I suppose, just to finish it off, but I could now answer what is the speed of this charged particle as it goes racing away here. And so it would have a 2 times Coulomb's constant Q squared. It would have a 2 Coulomb's constant Q squared there. That's when I bring the 2 over. Downstairs then would have an m and would have an x naught minus a there, and have an m x naught plus a here, square root of all of that, and there it is. There would be the equation for the velocity. Shall we try another one then? Same thing. Again and again and again, just so that I can bore you. No, just so you can see, it's the same thing over and over again. Yeah.
And is this assuming that your original charges aren't moving at all?
Yeah. Now the charges did not move.
Okay, so they're stationary.
What would be different if it did? Because we're going to get to one of those. It's just I'm building up to that. If it did, then what would happen over here would be I would have another kinetic energy for the other moving object. Right. All right, so now that we've done what I might call the simpler ones were point charges, let's go back to a ring.
What is cut out in a million pieces?
Could you tell me the potential along the axis of symmetry of a ring? And of course, why would I care about that? Because what could you give me? You could, well, that too, but I'll hang on to that one. But we could find the electric field along this axis, couldn't we? By taking its derivative. Which, by the way, we already did a couple chapters ago, so I hope we get the same thing we got back when we did Coulomb's law. And I think it'll be even easier than we did before. But we can find it, right? And what we couldn't have done before, it's going to be real easy, is what if this disk, or ring, excuse me, was charged positive, and we put another charge positive here. Actually, why don't we switch it up a little bit? We've been things pushed away. What if we put a negative charge way over here along the axis and let it go? How fast is it going when it gets here? But let's start with potential. Here's my ring. What's the potential in the center of the ring? Keep this picture in mind. Keep this formula in mind. Same idea that we did with Coulomb's law, which is the same idea you learned in your calculus class. Chop it up into an infinite number of pieces. And so let's find the potential from a ring. So if I maybe draw a picture here of a ring to get me started, I will go ahead and use a radius of A for the ring. I think that's what we did a couple chapters ago, so to be consistent, I'll have a ring. I'll have this axis of symmetry, which I will label as the x-axis, and so I hope my poor drawing looks like that to you, where I have a ring and I'm trying to draw an axis of symmetry. Notice, of course, it's three-dimensional, so this part of the ring is coming out of the board and then the other part of the ring is going into the board here. But there's my ring, and I can ask this question that if I were to look at the point P, could I have a formula for what the potential is at this point P? And so, like we did before, let's imagine chopping the ring into small little chunks. Each little chunk would have a small amount of charge on it. Call it, say, dq. And label the distance d as x. This little chunk, actually maybe I should point my arrowhead to where the A is pointing so you can see it, but I guess that doesn't matter. It's a radius of a ring. They're all radius r. But forgetting the whole ring for a second, just taking the ring, and I don't know if you noticed this clever design Don did. See a little piece of tape? That's the little chunk. Okay, so focus on just that little chunk here. But as I come off on this axis right here, how much potential do I get from just that piece of tape right there? No, not the whole ring, that's coming. But what would this equation become? Would say Coulomb's constant times dq, right? And that's how our calculus comes into play. I'm going to say I'm going to put a little bit of chunk of charge there. And how far away am I?
X.
I'm not x, right? And that's why the three-dimensional picture is really helpful. If I come over to here, this is x, but then I'm over radius a. So this would be x squared plus a squared to the 1/2 power, right? And so there's Pythagorean's theorem. How far away am I? And that is what I might call a dV. A little bit of potential. It's a small amount of potential which comes from a small amount of charge, exactly. And so I've kind of modified this equation by saying a little bit of charge makes a little bit of potential.
Does dV mean electric field?
No. If I took the derivative of the electric field with respect to x, that's not what this is saying.
Oh, okay.
This is just saying a little bit of charge. This is more like taking the derivative of the voltage with respect to charge.
Okay.
Yeah. So it's a differential. And that's not electric field. Okay. So, to get the total field for the ring, I would have to add up the potentials from all the little chunk of charges. And here what makes it a lot easier than we did with Coulomb's law is I don't have to worry about the angle or the direction between them when they're vectors. And that's what we had to do when we did the ring a couple of chapters ago. And so that's going to make it really simple to do. Because the advantage of this ring, and and why we pick it as our next example after we do a couple point charges, is because what could you say about all those chunks of charges on the ring?
All the same.
Yeah, they're all the same distance. And so as I look at what is a constant out here, x and a are a constant. And all I then have is an integral of dq. And this one, we had that discussion before. Maybe it's worth asking it again because somebody asked me about the limits, so maybe I should put those on here. But I said then, don't worry about the limits. What does this mean to you? Yeah, this is total charge. This says just add up all the chunks of charge till you get all the way around the ring. And so if we said that the ring had a charge of capital Q, then this would be just capital Q. If you want some limits here, you could say, well, you could start at the beginning and go 0 and start adding to it until you get to capital Q all the way around the ring. So this becomes, when you integrate it, becomes Q evaluated from 0 to capital Q. Whoever was asking me about limits. So whichever way you want to do, visually or with some limit, you're going to get a capital Q here, and you're going to get an x squared plus an a squared to the 1/2 power. And so there's kind of this first step. What is the potential from a ring? And that's the main thing I want to illustrate, because now as I follow up, I say, now I have this. I have the potential from a ring. Could I then get the electric field from the ring?
Derive it. With x.
Now let me emphasize, I have only found the potential on the axis of symmetry. So I can only ask for the electric field on the axis of symmetry. So I don't want to give any illusions that I found it everywhere like we did for that dipole on the grid. We had x and y. But I have found the potential only on the axis of symmetry. So if I were to ask what is the electric field on the axis of symmetry, I could go the electric field in the x direction and the electric field in the y direction. Why don't I start with the easy one? What is the electric field in the y direction? You say 0. Why do you say 0? Right. If we go back to our symmetry argument with Coulomb's law, we would say, look, all those electric field, the y components would all cancel off, and you're going to get 0. Agreed. But do you see that in the math too? Do you see that if I were to take the derivative with respect to y of this, it doesn't have a y in it. So what does the derivative become? 0, right? Okay, so not a surprise that the electric field in the y direction comes out to be 0, either from our Coulomb's law with our symmetry that we did before, or from the math where we're taking the derivative. The other one is getting the electric field by taking the derivative of that, so it would be minus the derivative with respect to x of, again, Coulomb's constant times the total charge on the ring, x squared plus a squared to the 1/2. I'll leave the negative there. I'll even put the Coulomb's constant and the charge Q, and so I need to take the derivative of that. Now remember, it's raised to a power, and you downstairs, I always think it's better to take the derivatives by moving it upstairs. So take the 1/2, move it upstairs, and it's a negative 1/2. So that becomes a negative 1/2, and then you subtract 1 from the exponent, which makes negative 3/2. And then go ahead and move it downstairs, so it's a positive number again. Now don't forget the chain rule, and so the chain rule is 2x, and notice it's in the numerator because I'm thinking of this as being up in the numerator. Again, notice that the 2 and the half cancel off, and even the 2 pluses, and again, hopefully not too much of a surprise, we end up with Coulomb's constant times the charge of the ring times x squared plus a squared to the 3/2 power, which is exactly the same value we got for the electric field back in chapter 23 when we did Coulomb's law. I think it was a little bit harder when we had to take the components and break it apart, but nonetheless, whichever way you want to get there, you have that tool, and that's the whole point here, that we have now 3 different ways to get to this electric field. We can either find out the potential and take its spatial derivative, or we can add up the chunks of charge and do Coulomb's law, or we can do Gauss's law until we get the electric field. And let's not forget the second half of this, of why we would care for the potential. If I were then to have this ring and then put a charge nearby it and let it go, it would move because of the electrical forces, and I could ask how fast is it? And so now let's ask that. Let's say I have this ring, and here's this ring, and as we said, let's just pretend the ring has a positive charge here. Just to be a little bit different, let's say that I have way over here, either left or right, I guess doesn't matter. Oh, let's go at least really, really far away. And say over here I have a negative charge Q. And probably not a surprise that if you let it go, the negative is going to be attracted to the positive, right? And since it's right on the axis of symmetry, and we just said that there would be an electric field along the axis of symmetry, it would get pulled in straight along the axis. And so it wouldn't actually hit the positive charges, it would just get pulled in straight like this. And it would probably go past it and then begin to, did you say oscillate? Yeah, and go back and forth. So a follow-up question might be, what's the frequency of oscillation? And at least for those of you who've done 123, you remember that's exactly what we did, kind of that first chapter of Physics 123. Write out the forces and find the frequency of oscillation as things go back and forth. So for those of you who haven't had 123, you will say that's, okay, not going to be on the task because that wouldn't be a fair question. But those of you in 123 better know how to do it. So maybe I can give you guys a special different test here and say, what's the frequency of oscillation as it goes back and forth? All right. So now we get into our conservation of energy. And again, hopefully you're seeing how simple it works once you get the potential. You either take the derivative to get the electric field, or you use conservation of energy. So maybe changing into black so you can kind of see this was one option. My other option then is to say initial energy is equal to final energy. And again, if I kind of work on this a little bit and I come back over here, just like I said, to be different, I'll start it with far away. I'll start it with far away and again, release it. So what's its initial kinetic energy? 0. I'm just going to let it go. What's its initial potential energy? So what does this equation say about the potential when you're really far away? Isn't it 0? And that kind of makes sense. I mean, you're not going to have any potential energy if you're really far away from it. All these equations right here, what does this say? When does your potential equal 0 here? What does R have to be? Yeah, really, really, really far away. So if you are really, really far away from all your charges, you have nothing but a bunch of zeros added together and you're going to get 0. So not a surprise that I will start off with 0 energy. I have no kinetic and I have no potential.
Aren't you starting at a distance x, or are you starting where that is?
Well, I'm gonna start way over here. So my total energy to start with is 0. Now, of course, it begins to move, and when it gets right here, right in the center of my ring, and I'm asking what is its speed, well, I would then have a kinetic energy. So that would kind of be the first term, that it would have a 1/2 mv squared. It would also then have a potential energy. And again, how do you get the potential energy? Well, you take the potential and multiply it by the charge. And so if I take my potential, which is Coulomb's constant times Q over x squared plus a squared to the 1/2 power, and I multiply it by a negative Q. The negative is going to be real important here, because obviously if this is going to come out to be 0 and this one's moving, this is positive, doesn't the other one have to be negative? And so what's happening is as it is getting closer, it is losing potential energy. It started with 0 potential energy and got closer and went down, 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 down. It went into negative numbers. So it's losing potential energy, electrical potential energy. And in the process, where does it go? to kinetic, right? By the way, you can now see mathematically that if you put a positive charge here, this wouldn't work, right? But fair enough, that's why physically, if you put a positive charge here, it wouldn't go there. Right? And so it doesn't work mathematically, and it doesn't match the world. Yeah.
It just feels wrong to not have any energy to start with, because you need potential energy to start a movement.
I know, but we did the same thing with gravity, didn't we? Remember those rocket problems? Where was the gravitational potential energy equal to 0? If we had the Earth, and we calculated the potential energy, it was negative G m1 m2 over r. Where is the potential energy equal 0? Way out away from the Earth, infinity. And as you got closer to the Earth, what happened to your potential energy? It decreased. It became negative, and that's all that's going on here. If this helps, I could do the same thing. Let's say I start on this tabletop. And I go, okay, my height to 0 is on the top of this table. It has 0 potential energy. If I lift it up, it gains potential energy. Ooh, that was loud. If I let it go down, it loses potential energy and gains kinetic, right? What if I miss the table? Yeah, now the potential energy went down to 0, and then what? Started going negative. There's nothing wrong with negatives. Negative is just below 0. And so 0 is just our choice. Right? And so there's our equation. Now, with a little bit of work, I can put Coulomb's constant, Q, x squared, a squared, 1/2, 2, m, square root, v. And I think I got the point across, but just in case I did you see what I did, right? I started with what's the potential from a single point. Add it together to get the whole ring. Once you have the ring, you can either take a derivative to get electric field, or you can use conservation energy to get speed. Somebody else already pointed out, what else could I do with this ring? And of course, what I was asking is I can use derivative to get the electric field, or I can use conservation of energy. But somebody said, couldn't you add up the ring to get a disk? Okay, fair enough. Let's do another one then. Could you tell me the electric field from a disk? Could you take a positive disk and start with a negative charge way out here, let it go, and it goes faster, 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 hits the disk? How fast is it going when it hits the center of the disk? Can you answer that? Let's give it a try. And obviously you can see we're building up. They're getting a little bit harder here. The geometry, but it's the same logic. If you know this, add it up. Question?
I'm confused on when you found the velocity. That velocity is at the point where you're in the middle of the ring.
Oh, thank you, thank you.
Or is it at the point P because you used X?
Oh, no, okay, fair enough. This equation right here is the potential anywhere on the x-axis. Okay, so on this side of the equation, I should have been a little more careful here. On this side of the equation, I used x as being infinite. So that's how I got a 0 over here. On this side of the equation, I was vague. I just left it as x. So this would actually be the velocity at any point x. At the center, I should keep going. X is 0. So at the center, and so the velocity at its center would then be that, yeah. Mm-hmm. All right, so again, leaving this up here, maybe even keeping this ring nearby. Let's put it over here. The voltage from a ring, the potential from a ring, I should say, is Coulomb's constant times capital Q over an x squared plus an a squared to the 1/2 power. let's go to a disk and ask, all right, how would I do this for a disk? Well, I guess if it helps, it's the same thing you saw a couple weeks ago. Think of a disk as a sum of a bunch of rings, right? And so maybe a front view would look like this. A small ring, a little bigger ring, a little bigger ring, a little bigger ring, a little bigger ring, and bigger and bigger and bigger until eventually we get the whole disk. I think last time we used capital R for the disk, so I'll stick to that and do a capital R. Let's find it for the disk. Now, I'm going to start here by saying, imagine one little ring. And of course in my drawing I'm coming out of the board here, so x-axis is out here. And I'm going to say then, what would be the potential from just one of the rings? That's why we've drawn it last time. And we said, you see that ring right there? That has a radius of little r? What would be the potential from that one? Well, I might write it as a dV. Because I'm going to eventually say this is the potential from a very, very thin ring, and I want to add up all my rings. And that would be equated to a dq, because there would be just a little bit of charge on here. Now here's where we have to be careful. It's not a dr. dr is the thickness of this ring. What does this A mean here? This is the radius of this ring. So here I would like to put x squared plus r squared to the 1/2 power, right? And so when you start adding things up using your calculus, I think one of the challenging things to think about is what is getting small. And so as I look at this equation and say, when I make the ring thinner and thinner and thinner and thinner and thinner, and I'm a distance out here, I'm not making this distance out here any smaller. This isn't going to 0. This is not a dx, right? But likewise, I'm not letting A go to 0. A is the radius of this. And so as this ring gets thinner and thinner and thinner, the radius doesn't change. So this doesn't become a dr. This is an r. You got to scan through here and go, what is going to 0 as it gets smaller and smaller? What in this equation? And of course, physically, it's the width of the ring. But the width of the ring's not in there. This is not the width of the ring. This is the radius of the ring. The width of the ring is related to how much charge is on it. This is what is going to 0. So the dq is there, going with the dv. Now once you figure that out, now I think you can do the integral. Although that too is going to be a little more challenging than the ring here, is I've got to say, all right, what then is the voltage of a disk? Well, it is a sum of voltages of a bunch of rings. And so I'm going to add up all these rings. Starting with a small one and getting bigger, 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 and bigger. All right. So here's my Coulomb's constant. I'll put the x squared plus r squared to the 1/2 here, and leave that alone there for a second, because I can focus a little bit more on this ring. We did this back in Coulomb's law. Remember the surface charge density, sigma? I'll put it over here, but if I kind of pull out this sigma and say this is the amount of charge per area. For starters here, let's just say that the charge on the disk is uniformly spread out. And so what I mean by that is we could take all the charge on the disk, divide it by all the area. That's one option. But we could also take a small area and the corresponding charge, And that's where it'll be useful, because what I really want to know in this equation is how much charge is on the ring. So I can think of this as how much charge is on the ring if I divide it by the area of that ring. So how do I get the area of that ring? Yeah. If it mentally, it helps me to think about cutting it and making it straight. Then it would be a rectangle. You get the area of a rectangle by length times width, right? So the length would be the circumference, and the width would be a dr. That's how the dr shows up in the equation. And so the length would be 2 pi r, and the width would be dr. And so if I move this to the other side of the equation, this becomes 2 pi r sigma dr. And now I've changed the idea of a small amount of charge to a small width of the ring, where each ring has a radius of r and has a width of dr, and everyone has the same surface charge density of sigma. And in this case, I'm going to add it up from the first ring that has a radius of 0 to the last ring that has a radius of capital R. And of course, I will look for anything that is a constant. So the 2 pi and Coulomb's constant are definitely a constant. Sigma, which I said let's be a constant now, because I'm going to modify that in just a second, but for now, let's say it is a constant. I'll pull it out in front. And then on the top I have r dr, and in the bottom I have x squared plus r squared to the 1/2. And so there would be using my calculus of saying, if I know it from a ring, a disk is nothing more than the sum of a bunch of rings. But knowing what each symbol is means you got to do what I keep saying. You got to be reading the math as you go along. You can't just kind of do the math and say, oh, I'm just going to change variables and blah, 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 blah. You got to see the picture of why things like this is the dq. Okay. Now, fortunately for me, that is a pretty easy integral. And I wanted to show you some tougher ones today. I might run out of time. Maybe I'll show you on Tuesday. We'll see how much struggling you do over the weekend, but we'll see here. But this becomes 2 pi Coulomb's constant times sigma. And that's, I believe, is just that. Since that looks like the chain rule, I think I just got to bring it up to the top. I should double check, right? Let's take the derivative of this. I would bring it downstairs to a negative 1/2. That's good. This would come out in front, negative 1/2. Then I would have a 2r. Oh, so I think I need a negative here. Negative. Maybe I better try the derivative. So I think it should have a negative in front. Oh, if I take the derivative of this, oh no. No, that'd be a 1/2, so no negative. No negative. Then I would have that. Then I would have a 2r. Good. Okay, so no negative. No negative. All right. All right, so that is the integral, checking by taking derivative, or you can do a u substitution. Okay? And then I want to evaluate it from 0 to r. And so this becomes 2 pi times Coulomb's constant times the sigma. When I put in an r for capital R for little r, I get x squared plus r squared to the 1/2 minus, I put in a 0, I get x. Yeah, right there. Might even say the absolute value of x. Okay? And that's the part I wanted to show you, that I can do this. I can add up a bunch of rings. Now, harder than the other ones I did, but what could I do with this? Well, we're back to here. Could you tell me the electric field along the axis of symmetry? Sure, this is the equation for the potential along the axis of symmetry. So, just like we did here, I'll erase it and start again. And just like we did here for speeds, I can use that information to then solve this for what is the electric field in the x direction, what is the electric field in the y direction. Now, of course, I can only do it along the axis of symmetry because that's all I have here, is the equation for the potential on the axis of symmetry. But knowing that this is on the axis of symmetry, I could take the derivative with respect to y. That's kind of boring. What am I going to get here? 0. Then, so as to be expected, I'm not going to get an electric field in the y direction. Makes the same sense as before. I only got x directions from the ring. You add a bunch of x directions together, you're only going to get x directions from the disk. The more interesting one here is I can then go negative the derivative with respect to x of all this 2 pi Coulomb's constant times, sigma. And then this gobbledygook here. X squared plus r squared to the 1/2 minus x. So when I go to take the derivative, obviously the constants out in front are unaffected. So I'll leave those. Let me go ahead and take this derivative first. The derivative of x is just 1. It's got a negative in front, but remember this negative goes with it. So I will put a 1 first. So I'm going to take that derivative and then put it before. Because then when I put the negative, there's the negative, I've got the derivative of this one. And this is the 1/2. Then I get an x squared plus an r squared to the 1/2. And then I get a 2x. And the 1/2 and the 2 cancel off.
Why did you switch them? Why is it 1 minus that instead of that minus?
Well, I took the derivative, but I used also that negative in there.
Oh, okay.
So that negative with that negative made a positive. And then I listed it first. Maybe I shouldn't have done that much, but that's the way we solved the equation 2 chapters ago. That's why I wanted to write it in that way. It's exactly the same equation we did when we did this disk back with Coulomb's law. Okay? And so again, not a surprise. Okay? Now, you probably are noticing something that I've said in 121, but it's more true in this course than in 121 and in 123. You need to work these out from fundamental principles. There's a lot of equations here. I hope nobody's planning on memorizing all these equations. Here's a disk. Here's a cylinder. Here's a ring. Here. Gonna kill you. That's not what physics is about. Physics is about learning how to work it out from the fundamental principles, knowing a point and working it out. Okay, and that gives us the power to do any shape, not just what we've done before. Okay, as I say before, nobody really wants to hire you to do something that's already been done. It's already been done. They want you to do something new, something different, something inventive. And so if it all becomes down to plug and chug, you'll do okay. You'll have an okay job. They'll need people to do plugs and chugs. And you'll have a okay life with an okay house. Okay spouse, okay kids, right? But it's not the next step, the real inventing of stuff, the, moving technology forward, the million and sometimes $1 billion ideas that come from going, what's the fundamental idea? What could I do? I'm tired of my cell phone having to be charged up once every 3 days. Maybe if I could just get that cell phone, instead of sending out radiation in every direction to find the cell tower, what if it just went the direction of the cell tower? And all that energy that goes out while I'm talking is not needed. And I only need a fraction, maybe about 1/100th of the energy to go to the cell tower. And so this phone that used to take 3 days to lose its charge is now going to last 100 times longer. And I only have to charge my phone one every 300 days. All because somebody figured out how to make the radiation from the phone go only in the direction of the tower. And hopefully not into my brain anymore. And hopefully not have brain cancer. And so not only will I have a phone that's going to last for 300 days without charging, I'm going to save a lot of brain cancer problems. And although you yourself may soon die of brain cancer, your kids won't. Okay? And that will be the invention. All right? So, I've said it many times, but and I sometimes even sillily, but hopefully you get the idea. All right. A lot more than just plug and chug here. Now, not done here, but I'm going to do the same thing. That, okay, now I've got this disk. I have now gotten the potential, which was a useful one, which led me to the electric field, but I can also ask the same question. What if this disk was, say, positively charged? And way over here somewhere, I had a negative charge along the axis, and I let it go. It starts from rest. It's going to go faster, 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 and eventually hit it. How fast is it going to go when it hits there? Because I know when it hits there, it gives off light. And of course, what kind of light depends on what I put here. So I'm going to need a little bit of distance. And if this was 40 years ago, that little bit of distance would have been a TV monitor that's probably about 24 inches long. And now I have a plasma TV that's only millimeters thick. But somebody is going to make it microns thick. And so instead of having this TV that used to fill my whole living room, I now have TVs I can hang on my wall. And you will have TVs that you will pull out of your pocket and roll out like a sheet of paper and watch it and roll it back up, because it's only going to be microns thin. Because you figured out how to accelerate it in a much shorter space than is needed. So let's give it a try here. How are we going to get this crazy electron, and what is it going to be at speed when it makes impact on this disk? And so again, maybe changing colors just to kind of illustrate the second step. Initial energy is equal to final energy. So the fundamental idea is right here, get the potential. From that you can get the electric field, or you can get the speed. And so coming back to this picture, I would have a negative charge way out here. Same as before. I would say I have 0 kinetic energy and 0 potential energy really far away. Now, I better stop and think about that one. I don't think this one's quite as obvious that it is 0 potential really far away. The other one was in the denominator, and when I had a big number in the denominator, I came up with 0. But I claim this does too. Can you see that? When this is x is really, really big, don't even worry about that number, right? When you make your millions of dollars, you will not care anymore about $2 or $3. It's just too much to care about that little one, right? And if you don't care about that one, then this becomes just an x minus an x is 0, and so really far away you should get 0. And that's not a surprise, because as we already said, the potential is 0 when you're really far away, and so if you add up any shaped object, you better get 0 when you are really, really, really far away, because that would be nothing but a bunch of points, a bunch of zeros added up. And so sure enough, like before, the total energy it starts with is 0. As it comes racing towards the disk, it will have a kinetic energy of 1/2 mv squared. When it gets near the disk, in fact, let's go all the way to the disk. When it was getting close, x would have some value, but when it gets all the way up and makes impact, what is the value of x? 0. So this is r squared to the 1/2, that's an r, and that's a 0, and so that means that the potential is 2 pi times Coulomb constant times the charge density times r. That would be the potential at x equals to 0. To get the potential energy, though, remember I have to multiply by this charge. So let's not forget to multiply by a negative q, and I'm going to add those together. And then, let me save a little bit of time, but a bunch of math will give you the velocity. Now, I say I wanted to make sure I did something else, because as I look at your homework, over the years I have got a lot of questions, and I would call this then the hardest one of this unit, number 63, or perhaps 62. I wanted to give you a hint towards both of them. I don't know if I'm going to have a time for both of them, but at least I'm going to do 63. And since it's only a hint, 5 minutes will be fine. Because what is different in 63 than what I did here? Let's read it here. It says, a disk of radius capital R has a non-uniform charge density on it. Other than that, it's the same, and it says, by direct integration, find the potential at a point P, a distance x, along the axis of symmetry. So it's the same problem, except can't take sigma out. So as you're doing the homework, start here, go to here, go to here, but now you can't go any further. They do tell you, though, that the charge density is some constant times the radius. So what they're really saying here is you have a disk that has no charge in the center, and as you move out, it gets more charged. So there's a lot of charge out here on the rim. Perhaps it is like a spinning disk. Spinning makes charges in rubbing. If you spin a disk, doesn't it rub on the air? Which part of this disk moves the greatest speed? Outside. So a spinning disk in the atmosphere will build up a charge here that is bigger than here because it is moving faster. And it will build it up with this relationship. And that's what they're kind of asking. Maybe this is blades on a helicopter. How much charge is going to build up? It's going to be the most on the tips of it. In fact, on a helicopter, it'll build up so much that it'll fly off, and the sparks will form. And so if you see this at night, especially with light amplifying goggles, you know, looks like a fireworks show as they're coming off the tips. And that's what this problem is referring to. A lot of times we have spinning disks. So the point here is you would get a C out here, and you would get an R squared there. I'll let you do the rest, because that's not an easy integral, but I can tell you, don't stress over doing the integral all on your own. Remember Appendix B's got all the integral tables listed there? It almost has that one. If you do a U substitution, then you will see it in there. If other than that, go ahead and go to any of your integral tables there. But the big issue here is not so much this integral as much as setting up that integral and understanding that integral. How about I give you a hint on 62? Nah, all right, 62. 62, again, can be a little bit of challenge, especially since I'm going to have to kind of summarize it real quick as we go through here. But listen to this problem here. It says a solid sphere of radius A has a uniform charge density ρ and a total charge Q. Now, carefully, is this an insulator or a conductor? It's an insulator. How do I know? It's got charge on the inside, right? What would a conductor do? Would all migrate to the outside. Okay, but this obviously is an insulator. Maybe that's not as important as just knowing that it has a charge density everywhere throughout. And it's uniform. Sounds easy, right? Derive an expression for the total electric potential. In other words, how much energy would it take to assemble this ball? And so if this little tiny ball is in our little microprocessor, what we have to do is we have to put a little charge in the center of the ball. And then more, and then more, and then more, and then more, and then more. But the problem is, once you put that first charge on the ball, isn't it hard to get the next charge on? So imagine yourself. Here's the whole ball. Let's say that you have charged this much of the ball already. So you start funneling in charges. How much would it take just to bring one more fraction of a charge in there? Well, I guess I'm saying du would be dq times the voltage at that point, right? That's our fundamental lesson, right? A little bit of charge brought into the potential. So whatever potential is then created by the charges that are there would be this term. And then I'm bringing in a dq. That's how much little charge it would take. And of course, then if I added that all the way up, I would get the whole ball, right? So again, the real key to this problem is to realize two steps. Number one is, how do I figure out what the energy is to bring in just one little charge once it's kind of partway charged there? And then to realize that I would think about this from a beginning point and add more charge until I got to my end point. All right, so the first part of it, the integral of dq, is pretty self-obvious. But what's this? Well, this is the potential from a ball. Now, it's a ball that's fully charged. Here's where I wish I had a little bit more. But whether it is the charge on the surface or all the way through, we saw this with Coulomb's law, we get the same electric field on the outside. The potential is the integral of the electric field, so you're going to get the same equation for the potential. So this would be Coulomb's constant times the charge that is on the ball at this moment. Now, that's not the total charge of the ball, but the charge on that moment divided by its radius, right? Now, the total charge at that moment would be the charge density, rho, times the volume of that ball, 4/3 pi r cubed. That's how much charge I have, divided by r. And one more helpful hint, I'll leave this alone. How much charge am I bringing on? Well, I'm going to bring a charge that would be the volume of a little shell times the charge density. So that's going to be another rho for charge density, and the volume of a shell, 4 pi r squared, dr. Yay! And there's my dr, adding from 0 to big ball. And even these magenta ones only take 3 minutes. It'll be fine. Right? All right, well, good luck.